Следующий доклад у нас перед сессией обсуждения результатов этой темы. Доклад Джеймса Дуайера «Ошибки оснащения птицезащитными устройствами, расширение защиты пернатых хищников за счет реализации предотвращения столкновения и управления электроподстанциями».
Hi, thank you for coming. Thank you for being here, and thank you also to the Altai Project and to Elvira for making this possible. We appreciate it. I'll be talking to you today about preventing avian electrocutions, and then we'll also switch to talk about collisions. So a very brief introduction, just one slide on the introduction, because I assume most of you know how this works. Electrocutions occur when birds become part of an electrical circuit. The odds, increase with biological factors. So the larger the bird, the higher the probability that the bird will make simultaneous contact between an energized wire and either another energized wire or a path to ground. Configuration also plays into electrocution risk because, as Rick showed you before, when poles are grounded, the separations between phase to ground are small, and so electrocution risks increase. And electrocution risks also increase when the habitat is good. So there are birds in the area. So that's a very brief introduction because, again, as I said, I assume you mostly know this stuff. Now we're going to talk to you today about retrofitting errors. And the idea behind that is to help you understand, to think about if we understand what's wrong with retrofitting as we work our way through a power line system, then we can know how we want to solve those mistakes so that we don't have electrocutions continuing. So we'll be drawing examples today from a couple of papers we've published, one from the US and one from the Caribbean, and also from pictures that Elvira sent me and pictures that I found in Russian and Kazakhstan publications. We'll go through 5 types of errors, and then I'll show you pictures of them, and then we'll transition to you being able to look at other pictures and think about what errors you see. So we have product design errors where the product does not fully cover all the energized components that it's intended to. We also have mitigation plan errors where the products are good, but not all the potentially dangerous points on a power pole are identified or addressed, and so electrocution risks persist. We have application errors where the products are good, but they're not installed correctly. We have improvisation errors where the product might not exist to suit the need, or perhaps the product is not on the truck, and so the lineman needs to do something, and so they improvise. Oops, the last one. And we have maintenance errors where for some reason the product might have been good and might have been installed correctly, but has been removed and then not reinstalled. So here are some examples. In A, B, and C, we see product design errors. So in A, the plastic cover does not completely cover the top of that metal energized switch or cutout, and so electrocution risk persists. In B and C, we have covers that have fallen off, and we argue that if the cover can fall off, then it was not designed well in the first place. Here's another product design error where we were experimenting with perch deterrents and monitoring that with remote cameras. And we could see that when we put perch deterrents on power poles, we're not always good at manipulating where birds go, and we can sometimes push them into energized parts instead of away. So we consider perch deterrents in many situations to be an error, although perch deterrents can be useful in some situations. Here's a picture from a Russian publication where we see a product design error. This conductor cover has a hole in it, and a bird can still reach into that and contact energized wire underneath the cover. Here we have mitigation plan errors in D, E, and F. So in D, the center conductor is not covered. In E, the ground wire below the arrestor is routed near a conductor. And in F, we are missing a dead end cover. So all of those are mitigation plan errors where we have solutions for those risk points, but they were not applied. Here are a couple more mitigation plan errors. So in A and B, the jumper wires are covered, but none of the equipment parts are covered, so electrocution risk persists. In C, some of the jumpers are covered and some are not. So as we just saw in the previous presentation, mitigation plan errors, if we're looking at the cross arm here, we're thinking of design errors, but on the top is a mitigation plan error where even if the cross arm approach had worked, we omit the risk at the top. So that's a mitigation plan error. Here we have D, E, and F where we have additional application, or we have application errors where we have a switch open on D, so the energized switch blade is very close to a grounded arrestor ground. And then on E, this is a very common problem we see where the jumper is covered and the arrestor is covered, but in between is a tiny bit of exposed wire. And we see over and over again that those little bits of exposed wire lead to ongoing electrocutions. So we think we've retrofitted the pole or the pylon, but we have not. And in F, we have two pieces of covered jumpers connected with a metal clamp that is not covered. So electrocution risk persists there as well. Here are a couple other application errors where bushing covers are installed incorrectly. So this one's too low and these are too high. So it's important to maintain the integrity of the electric system that we install these correctly. Here's another application error where we have presumably a good cover, but we also have a bunch of metal there that is exposed. So that should have been dealt with differently when the cover was installed. We also see improvisation errors. So here are a few from the Caribbean where the electric utility lineman had scraps of material that he wanted to use, and he had jumpers that he recognized were dangerous, so he used the scraps on the jumpers, but there are gaps and cracks in those covers, so electrocutions continue there. The same occurs here. He didn't have enough material, so there's a gap there. And here this was rigged to reduce that risk, but it's almost certainly going to fall off. So those are improvisation errors where the person installing it had a good intention and wanted to do the best he could with what he had on his truck, but we haven't provided him with the equipment that he really needs to do his job well. Here's an improvisation error from this area, where, as we saw in an earlier presentation, we have a plastic cap on there. It shows good intent, but it's not likely to last very long. These are maintenance errors. So here we're in a substation that was at one point fully retrofitted to be safe for animals, but these covers are lying on the ground instead of up there on the equipment. So at some point, somebody had to take them off to do maintenance and chose not to put them back on. So those are our error types. And now we'll go through some examples of errors. Or I'm sorry, we'll give you the opportunity to look at these. So there's an error on this pole. And you can think about, what do you see? Do you see a product design error, a mitigation plan error, an application error, an improvisation error, or a maintenance error? So what we have here is an application error, and it's that exact same thing I showed you before where the jumper is covered and the equipment is covered, but in between is a little gap. You can see that exposed metal, and a bird that fledged from this nest landed on that capacitor bank and was electrocuted. Here's another poll where you can think to yourself, what errors do you see? And in this case, what we're looking at are mitigation plan errors. So the jumpers are covered, but none of the other equipment is covered. The center conductor is not covered. So a great deal of electrocution risk persists on this pole. So this one is from this area, and we're not really sure what kind of error we're seeing because we're not as familiar with these products, but we can see that a piece has come off and a piece is loose. And when we look at this, our experience from the US is that these little zip ties in the US don't tend to last very long. So our concern when we see this is that maybe the approach for installing them could be improved, but we don't know that for sure because we're not as familiar with these products. So that's why the error is in orange, not in red. Maybe this is a product design error, or maybe it was installed incorrectly. And here it is again with some different structures where we have it slip down the power line. We see the exact same thing in the US. It happens everywhere. And we wonder, is this a product design error or an application error? And the same here. we wonder, why did this piece come off? Is it related to the use of zip ties? So this type of error should be intuitive to you, right? So there's almost exactly matches the example. We have an improvisation error where, of course, the person working wanted to do the best they could. They didn't have the materials they needed, so they improvised. Here's another error, and you can see we have here an application error. So the equipment looks good. Everything's covered. Bushings are covered, arresters are covered, or switches, I'm sorry. Wires are covered, but right here is a gap where this jumper connects there, and you can just make out a little bit of exposed metal. And so, yes, it is true electrocution will be reduced, but if you have enough birds perching on this power pole, eventually an electrocution will occur even though these covers are there, because there is this application error. So two types of errors here, where we have the product design error here, as we heard about in the last presentation, and then the mitigation plan error where there's not much focus to address the center phase. Here's some more errors. I'll give you a second to think about which errors you're looking at. So there's a suite of potential ways to categorize these errors. We don't really know which because we're not as familiar with these products, but we have gaps under the covers. You can see the exposed metal. And so was the product not suitable for this placement, or was it not installed correctly? We don't know, but clearly there is some type of error there. It could be an improvisation error, we don't necessarily know. And then we're not covering these dead ends. So a bird could be electrocuted from the phase to ground there if it works its way onto the insulator. So that's a mitigation plan error. So we want to cover these jumpers completely, not just partially, and we want to cover these dead ends. Another one, what error do you see here? So I see a mitigation plan error. The jumpers are covered, but the tops of these switches are not, and electrocution risk can persist either phase to phase or phase to ground. Another set of errors here where we have the covers attached with zip ties. They're covering these dual insulators, but we don't know, should the cover have been designed to extend there and it wasn't, or was it not installed? So we don't know which type of error we're seeing, but we do know that we'd like to see the cover go further out on all 6 of these wires. Here's another error where this might be a good idea, but it doesn't extend far enough. So the similar concept that we saw half an hour ago from Andrew Dixon showed that the cover went all the way across the cross arm. And so that seems like a better solution, but this one is too short. And here we don't have a cover on the top. So in this case, we have a cover on the top now, but we're not covering the cross arm. So we still have phase to ground risk at every phase and phase to phase risk here. Another one. So you can see these errors from this area. We're not covering the whole jumpers. We're not covering this jumper at all. There are gaps in that coverage. So we still have phase to phase and phase to ground risk. And exactly which error type is hard to say. Was the equipment not designed for this type? And was there a different type of equipment available, or was it misinstalled? So here we have the suspended insulator, which is great for the outer conductors, but we can still get electrocution risk here. So which kind of error is it? It's hard to say. We could put a cap there to reduce that risk. We saw these in the previous presentation. So we have these product design errors here where the energized equipment is still exposed. And then we have the mitigation plan error in the center where that's not addressed at all. These from the States, where we sometimes see perch deterrents used extensively. If they're not paired with conductor covers, then we can still have electrocutions. So we see the use of perch deterrents as an error type, unless it's a specific situation where covers don't fit. So I'll give you a second to look at this pylon and try to identify the errors. And I don't see any on this pylon from this angle. From a different angle, we might see the error here if it were there, but overall, this pylon looks very good. So that's filling in some more on electrocution. And now we'll talk a bit about collisions. And the reason for that is because when we were looking at electrocution papers from this area, from Russia and Kazakhstan, what I noticed in some of the reports was it appeared that people were walking power lines and recording carcasses, but some of the carcasses were under the pylons and some of the carcasses were mid-span. So the pylon carcasses were likely electrocution, but the mid-span carcasses were likely collision. And those were not separated in the papers, but the problems that lead to those different types, locations of carcasses are different, and the solutions are different. So we need to understand collisions as well as electrocutions to solve the whole problem. So most collisions occur at night or in periods of bad lighting. That's not true for all species. If you have bustards, they're at risk during the day. There are some other species like that, but most collisions occur at night. They can also occur when fog or precipitation make it difficult to see pylons. Most collisions are also thought to involve large birds like cranes or bustards, those kinds of things. But we find that when we carefully walk power lines and look for small birds, we also find them. So passerines are also commonly involved in collisions. They're just much more difficult to see. And so we have a detection bias that makes us think big birds are more susceptible to collisions, but in fact, small birds can be as well. So here's an example of what a collision can look like. There'll be three birds coming in. So there's the collision. These are cormorants in the US.
Yep.
And you can see this bird walking away. So when we do collision studies, one of the things we have to consider is, did we actually find all the birds that collided, or were some injured and then died later? Here's another look at collisions. In this case, the line is marked. It didn't play. Can you hit, excuse me, can you hit enter? Can you play the video? No. One collision, two, three collisions. There are four total, and you can see that line is marked. But the marking is not sufficient, even though it is marked. And so we can ask ourselves, how are these collisions occurring when lines are marked? We'll come back to that. I'll show you some other videos. Before we transition, I'll just show you that there are also collisions in this region. So these collisions are from Iran. You can see a pile of birds there. Flamingos collisions in Iran, gull collisions in Iran, pelicans, herons, other birds. So collisions are an issue here too. They just don't seem to be as well reported. So we need to prevent them, and we can talk about how to do that here. So often we talk about we could put the lines underground, which is great if it's possible, but in many cases it's not possible or it's too expensive. We can talk about shielding lines with trees or terrain, but in real life that's generally not practical. The power lines are where they are, and we have to deal with them where they are. We can talk about removing the overhead shield wire. Generally, the overhead shield wire is about half the diameter of the conductors, and it doesn't have any current in it, so it's not creating corona. So it's harder for birds to detect. So most collisions involve the overhead shield wire, and if you could remove it, that would probably solve most problems. But it's there because we need it. We need that overhead shield wire to protect the electric system from lightning strikes. So we can't remove it. And that leaves us with this. We tend to try to manage collisions by marking power lines. And I'll show you some pictures of these line markers. The next video will be of these and then some of these. So here you're now in a drone and you're looking at a marked power line on a gray day when collisions tend to occur. So when we're out there looking at power lines, we tend to be out there on good days, looking up at blue sky. And line markers seem really clear and bold. I'll show you some. But to a bird, that may not be the case. So did you watch that video and you could see that as you went into the bird's position, you couldn't see the power line anymore, even though it was marked with these. So in our hands and looking up at it from below on a blue sky, these seem great. But in real life, maybe they're not so great. Okay. So like, same for Rick, he's not bringing those home. I'm not bringing my line markers home either. You can have them. I'll show you another video. So in this case, you're again in a drone and you're flying toward a power line. So you're pretending to be a bird. The line is marked. And you can ask yourself, at what point do I see the line? And do I see it with enough time to respond? So this span is marked with the spiral, the same as what was on the previous line. And you can ask, do you see the spiral yet? I just now see it, but it's because I know where it is. Now we're one span away in the same conditions, and that span is marked with these ones. And you can see that you could notice it right away. So the type of line marker we use matters. And these are free, you can have these as well. So we can talk to you about collision, and also there are many resources on the internet, and you don't need to memorize this slide, but you can know that if you reach out to us at EDM, either Rick or I or other people who work on these issues, you can find resources to help you understand the problem and how to mitigate it. So what we think the future of line marking is probably with drones. Historically, we've marked with bucket trucks or hot sticks, and that works great if you can reach the power line. But in many cases, we can't because the high-risk areas cross water or the transmission lines are energized and we can't reach around the conductors to get at the shield wire with a bucket truck. So the alternative in the States is to install line markers with helicopters, but that is expensive, time-consuming, and potentially dangerous. So this is probably the future of line marking. You can see there's 8 examples here. There's maybe 10 or 15 total on the market at the moment. Lots of different drone companies coming out with ways to install various types of line markers. So we have a variety of the drone companies can install these ones, the Fireflies, with either moving parts or not. This is a brand new one that's just on the market, and it's made by a company that also makes the drone. So this is the first one where the intent of this is to be installed by a drone. So I'll put these out and you're welcome to take them with you. I have a few of each. Just if you play with them, understand that this is a really strong spring, so watch your fingers. Here's a couple pictures of various drones installing line markers. So approaching the wire from the side and departing from the side is how this drone works. This one approaches from below and then escapes below. And this one approaches from the side and then escapes upward. So different ways of doing the same job. Really, the usefulness depends on the configuration of the power line. In addition to line marking, we can consider alternative solutions. So we'll talk about the avian collision avoidance system, which is a product we've developed at EDM where we're using UV light to illuminate power lines. And the thinking behind it is that at least some birds can see UV light, ultraviolet light, but people don't see it. So if we could shine that on a power line, we could potentially shine a giant spotlight on the power line so birds can see that line at night, but people don't. So here's what that looks like. You can just barely make out some purple light here, but to a bird that might be a giant spotlight. It depends on the species. Here's another look at it. This is how it looks to us. And then if we leave the shutter on the camera open a long time, this is how we think it might look to a bird, but we're not birds, so we don't exactly know. The ACAS is composed of some lights, some boxes that control the lights, solar panels to power it, and batteries. And when we install it, you can see it's relatively compact. And the idea is that maybe it will help solve collision issues. So we did some studies with this. We happened to study it only on marked lines because in each case where we were asked to use it, people had already tried the best available solutions, various types of line markers, but that hadn't worked. So then they called for the ACAS. And what we found is the ACAS almost completely eliminated collisions when we illuminated power lines with it. We did a study of just one line, and then we sold ACAS units to the Audubon Society, which is an NGO in the US that is focused on bird conservation. And they studied not just the power line they illuminated, but also another power line 2 kilometers away, crossing the same river. And they found that when either line was illuminated, collisions were reduced on both power lines. We also did a similar study in Colorado where we illuminated one span, but monitored bird movements across 3/4 of a kilometer in each direction from that span, and found that birds avoided the power line over the whole length. So it looks like it could be a potential solution. We've focused our studies on cranes so far, but we look forward to expanding our studies and focusing on others. So that's electrocutions and collisions. And then one more brief topic, we'll talk about substations, because we also see raptor electrocutions in substations. So raptors can be attracted to substations either as nesting sites or because there are birds there or small mammals there that the raptors want to hunt. So the solutions then are, first, remove the prey. So here we have a starling and here a rabbit. And if we can make the substation less attractive to those creatures, then it becomes less attractive to raptors. So to do that, we simply make sure our fences are good and remove any trash or junk or nest sites from the substation so that small animals, potential prey items, are not drawn there. So very simple solutions. Same here, if we just make sure the fences are good, we can keep animals out and then we're not attracting raptors in. We remove the passenger nests, ideally after they've nested. We can remove them from transformers, from the substation infrastructure, from equipment. As long as we remove those nests, we're reducing the attraction to raptors. So that's a simple thing that electric utilities typically want to do anyway. And then we apply the techniques that we know to apply from pylons. Cover energized wires, cover equipment, so that birds cannot contact anything energized when they're in the substations. So we'd like to remove the attractiveness up to the substation to the raptor and also make the substation less dangerous by covering energized equipment and by making sure that we cover it well, we don't leave any gaps. So it's all the same lessons as we get from pylons. We can also install discs to prevent contacts between the energized components and the metal rack that holds the substation, or those components. So that's my presentation. And if you have questions, you're welcome to contact us. You can also look up this video, which is a video about raptor electrocution work, where you can learn more about it that way as well. I don't know where we stand on time, but I'll take questions if you have them. And again, you're welcome to have these.